Hey, Joey, are you there?
Yeah, hey,
Well, how's it going with you?
pretty good so far. Yeah,
Good. Well, tell me how the last class went. How'd it go?
uh, good. We didn't the calc class.
Hmm.
Oh yeah, I finished with a B plus, which is right what I was hoping for. So that's really good.
Good.
I ended up I think I got an 88 on the final.
Oh man, that's so
I
close, isn't
missed.
it?
Yeah, I know.
To the A minus. But
Yeah,
hey, you did quite a great job with those problems we were
yeah,
working on. So that's a quite accomplishment.
yeah. I'm really happy with how it went. So,
Good, good. So what was that made the difference for you, you think?
um, I think there was a couple like some of the types of problems where you showed me like a shortcut or just a way that like our professor taught us like a different way that I don't know, didn't really click, I guess. And then the way that you showed just seemed to be better. And just all the extra practice and like, I don't know, maybe learning more of once I conceptually grasped like what was going on, then it was much easier to like visualize the problem and
Right. When you get
attack it.
that good foundation,
Yeah,
understanding what's going on, man, it just makes things click, doesn't it?
yeah, definitely.
Well, Julie, I'm excited for you. That's awesome. Getting a good B plus, to kind of competitive school you're at. That's good accomplishment.
Yeah, yeah, definitely.
All right. Now, what class are you in this term?
Linear algebra.
Linear
Uh,
algebra.
yeah,
Fun times.
yeah.
W- Have you heard any rumors about linear algebra or?
Um, Not really. I mean, buddy, I've had a couple friends who took it, and I mean, they said it wasn't easy, but it was. They liked it better than calculus, so I don't know.
I, yeah, I kind of like a little better in calculus too. Um, it's a little bit complicated at first trying to put
Yeah,
things together because here's kind of the deal. All this time you're doing things in pre-calculus, go Cal 1, Cal 2, Cal 3, differential equations, and it's all leading up to one thing to the next. So one class really
yeah,
feeds into the next. When you take linear algebra, it doesn't matter if you take calculus or not, because you're not
yeah,
going to be integrating or differentiating her at all in the course. So that skill set's not going to be there, but the skill set you are developing in your calculus courses is the mathematical maturity that you're going to need in order to do well in a linear algebra class. That's why. Well, that's one reason those classes can help you in that regard. But yeah, it's a fun class once you get the hang of it. I took that class a while back, many moons now. But when I took it, I kind of struggled at first, and then it took me a while to understand why was I struggling so much with it. And then once I realized and saw the beauty of it, I was like, man, I'm gonna get my dissertation in this. I love this class. I'm going
yeah.
for it all the way. But what book are you using for this course?
Um, it's it should be it's linear algebra and its applications, sixth edition by David C. Lay, Stephen R. Lay, and Judy J. McDonald.
Yeah, I know Judy.
Yeah,
Oh yeah. Yeah, let's see. You have which edition?
sixth.
Sixth edition. So is it this one right here?
Yeah, that's it.
Okay, so here's what I wrote.
Uh-huh.
Maybe I turn around that way you see a little easier.
Oh yeah.
Okay. So if you open this up and you flip a few pages into it, second name right there.
Oh yeah.
I know Judy.
That's awesome.
So she was actually at my PhD committee. And I remember when she was helping write this book. It's been around a long time. It's been around for like 20 plus years, honestly. Like the second edition, third edition.
Yeah.
And I think I used maybe the second edition when I was an undergraduate. But I think it was like the fourth. for fifth edition, she started jumping on board. She's doing the solution set, and then uh, it just kind of merged into this new version where they do a lot more things in terms of data science. So it's kind of geared a little bit more towards in that direction, which is really good. Um, so if that's something like you want to do later in life, this course will help you make a good transition, a career switch if you wanted to. So,
Yeah.
uh, but linear algebra, there's so many applications. What I love about it is I consider it like a hub of mathematics. You can go purely theoretical, like discrete math side of things, or you do more applications like a calculus side of things if you really, really wanted to. There's just so many different ways you can go with these kind of courses.
Yeah.
So, did the class already start for you?
Yeah, so we didn't we did we didn't do a ton of content in our last class. Um, but I have it later today, where
Okay,
I
so
think
you have it on
we'll
Tuesdays
start.
and Thursdays, or
Yeah, Tuesdays and
okay,
Thursdays. But I mean we have our first homework already. It's not due for until next week, but I mean we can look at some of those problems, I guess.
yeah,
But
let's take a
we
look
haven't
at
really
some of
been.
these. Now, are they giving you them out of the textbook, or are they just
So
giving you some additional problems?
we have two types. We have written homeworks and then online homeworks, and the written ones are out of the textbook. Um, and then the online ones are just they're not from the textbook, but they go along with it.
Okay.
So
Now, do you have some stuff from the textbook you want to look at, or some written stuff you want to look at?
we can go through the ones in the textbook, I suppose.
Sounds good. Let's see what I have here. Now, honestly, when you look at the different versions of the textbook, they don't really change up that much. The sixth edition actually does change up a little more in this one. So if you're doing some certain topics, which are going to be in the sixth, which are not in the fourth and the fifth, but really the second, third, fourth, and fifth edition, they're all about the same. So if you wanted to like, save yourself a few bucks, if you're taking that class or using those books, I would say find a cheap one.
Yeah.
What they do is they change up the numbers on the homework problems to saying two, they might say five, and maybe instead of saying 2x plus 3, they might say 5x plus 7. That's the same idea.
Right. Yeah.
Okay. So here's the fifth edition. It's a little previous one. I'm not sure if I have the six on a digital copy. I might.
I have it on a digital, but
Sure, you can drop that link over here. I'll take a look and see what you got.
I don't know if yeah, I don't. Well, it's through like Pearson,
Oh, okay.
so but I mean, I can just screenshot the problems that we're supposed to do.
Yeah, that'd be great. Why don't you go and do that and drop them over here on the bit paper and we'll take a look at them. Now, in this class, are they going to allow you to use a calculator or not?
They said we can on like homeworks and stuff, but we can't on exams.
Okay.
Do you
So
have the link?
what you would need to do is get very proficient at row operations. That's going to be your bread and butter in the class. Now, do you still have the link for the bit paper?
Yeah, I think I just put it in loading.
All right. Love this problem, Joey. All these problems, by the way. Anyways, find the equation G, H, and K that makes this augmented matrix correspond to a consistent system. Wow. Now, in linear algebra, unlike other classes, it is completely different. And one of the reasons why it's different, besides the fact that you don't have to like derivatives of integration, but you could, roundabout ways, use a matrix to do derivatives of integration, and we might talk about that later, but is you have to know terms. You have to know the jargon. It's just one of those things you just kind of going to have to do. Because if I start talking about consistency and augmented matrices, and if you don't know what I'm talking about, man, you can't work the problem. So you have to know definitions. When you're taking a calculus class, did you have to know the definition for a derivative or definition for a limit? I mean, you could, like for every epsilon greater than zero, you didn't really need to know this. You just show me how that works for the most part.
Yeah.
Okay, that's not so much the case in this course. So there are certain terms that you need to sit down and actually know the definition for. What does it mean to be consistent? That's one of the definitions that's been used quite a bit. And if you don't know the jargon, and you can't solve the problems. Okay. Now, a lot of students, they're not going to realize that until about halfway through the semester and take the midterm and it's getting to the point of no return. They're not going to do well in the class because they didn't know the definitions. But you know you need to know the definitions, so you start off right now. So augmented matrices is one of them. And an augmented matrix is whenever I'm looking at a system, AX equals B, and I'm going to take this, I'm going to recalibrate it so it looks like this. Now, here, you don't really need to have that line. That line is just really there as a visual reminder about how you're going to go about these given problems. You can put it in or not, but it is going to be the vector on the other side when I'm looking at my system. See, the question that you're going to be exploring for the next 3 weeks is solutions. What can I say about them and how do I actually compute them? The very first thing is you look at this idea of consistency. So if I say something's consistent, forget about the math for a second. What does the word consistent mean to you?
It's like always the same. It's the same.
Always the same. No contradictions, right?
Yeah.
Okay. Something you can kind of rely on. It's there. So when I'm talking about a consistent system, it has some that kind of same ideas. Now, that doesn't mean it's always the same, but there's no contradictions. If I was to give you something in the second dimension, and I said, here's a system of equations. Well, in the second dimension, linear equations corresponds to lines.
Mm-hmm.
How would I know if it corresponds to a consistent system? I got to have a common point of intersection, at least one. So if I have a point of intersection, the system's solvable. If I have lines which are parallel, it's not solvable. See, if I have something like y equals 2x plus 1 and y equals 2x minus 3, if I try to solve this system, I'm going to see very quickly that negative 3 equals 1, and that's ridiculous. It's inconsistent. So for consistencies, what I'm going to need is a common point of intersection. Now, I can use one point of intersection, or I can have an infinite amount of points of intersection. Now, if I have an infinite amount of intersection points, what that means here in the second dimension in R2, that means this is the exact same line. It's collinear. Something maybe like this. In order for this to be intersecting in the second dimension, here's all we really need, just really different slopes. And it's going to collide eventually. Now, Joey, take this into the third dimension. what does it mean to have solutions in the third dimension? First off, we're talking about matrices, and that corresponds to linear systems, as you know. When I'm talking about linear systems in the third dimension, I'm looking at things such as AX, BY, CZ equals 0. Think back to calculus 3. What was that? It's a plane. So when looking at linear equations in the third dimension, I'm talking about lines, planes, and automobiles. No. That's a movie. Maybe it's a movie. So we're talking about lines, and we are talking about these planes. And once again, what's plane? Piece of paper. You can think of it like that. So in order for a solution to exist in the third dimension, now it's helpful to think about this from a geometric perspective for the second and third dimension. Because what happens when you get to the fourth dimension? I don't know. So if I have an understanding of the second and third, might be able to stumble a little bit maybe into the fourth, think about it, and get out as fast as I can because it's really confusing, I guess. But there's two planes, two pieces of paper. And you can see how they're all coming together at this single spot.
Yeah.
Joey, it's like your textbook. It is linear algebra. Linear algebra textbook is linear algebra. Here's your plane. Here's your other plane. And they're all coming together at a single binding. That's your common point of intersection. So I can look at a geometric shape, maybe something like this, and that would correspond to a consistent system when I'm talking about two planes. But what if I took another plane, and I did something like this to it? Okay, so up top up here, they're coming together. Down here, they're not, just at these two places.
Yeah.
So in order for it to be consistent, they gotta all come together at a single spot, at least one point. So this right here represents an inconsistent system. Now, if I put the book like this, I can see right back here, that's a point of consistency. Everything's coming together. Look in the corner of your room, like maybe way up top. You see you have the ceiling and you got the walls. That point, that's going to be a solution for your system. It's like the coordinates of X and Y and Z. When we look at that coordinate planes, right there at the origin, that's consistency. Now, if I want something that's maybe inconsistent again, maybe I'll take my planes and I'll make them parallel planes. And we talked a lot about how planes are parallel back in calculus 3. Now I can take all my planes too and I can put them on top of one another. Linear algebra. You'll see that linear algebra is actually everywhere. It's like we actually live in a matrix. It's like a conspiracy theory. But I can put all my planes together and now it consists of a consistent system. So when I'm looking for consistency, I just want to make sure that things are going to work out. I'm not going to get something that's error or ridiculous. It's all there. It's not erroneous and whatnot. Now, here's the question. When I take this and I start reducing this matrix down, what do I have to avoid to ensure that I have consistency? Well, first off, when I do row operations, there are three different types. You can do scalings, you can switch up a row, and then you can add rows. And what do the rows represent again when looking at your system? If I was going to give you this right here, if I had this system, how would it express this in terms of a matrix system?
When you just have 4, 3, 5, and then 2, 7. Yeah.
Yeah, this right here would be something called your coefficient matrix. You have your vector B, and X will load up with X1, X2. And if I want an augmented matrix, I have 4, 3, 5, 2, minus 7, then 8. Now, as you go about your evaluations, determine if it's going to be consistent or not, you're trying to avoid situations in which you get something that's ridiculous. Let's just look at a real basic example. If you have x1, 5x2 equals 2, 4x1 plus 5x2 equals 3. Okay. I can write my augmented system fairly quickly. Each row corresponds to an equation, and each column corresponds to the coefficients for the variable. If I take the first row and multiply it by -1, add down, I get this. And if I was to reinterpret the results of the matrix, the last row is state. Remember, these are the coefficients for x1. These are the coefficients for x2. And each row corresponds to an equation. So it equals 1. 0 equals 1. That's inconsistent. Doesn't make sense. So what you have to do is you want to avoid situations in which you have a bunch of zeros and something that's not 0 on the other side to be consistent. Okay, let's go through this here together. How would you reproduce it? Here's what I would do. I might take the first row and multiply it by 2.
Yeah.
I'll leave the second row alone. And then I would take the results of my new row 1 and I would add it down to row 3. Now, when I do that, it's going to get me a 0, -8, 5, -3, -9, 14, 5, and then 2g, and then k. And would you look at that? It's like it's made for this. Take the second row now, add it to the third. So you can maneuver this however you like. Row operations, it's one of those topics which is, yeah, it's pretty obvious. You know, like I understand it, but it's also confusing, truthfully, because you understand how to add, you understand how to multiply, you can do all these things, but can you do them all at once 13 times at the same time? Okay, so that's where you have to spend some time going through the skill set, just making sure that you're proficient at it. So here you take an add down 0, 0, 0, and this entry 2gk plus h. Now, row operations, I can always go back to the previous one. They are reversible. There's my system. So I'm not going to get anything of inconsistencies up here. The only time I would get something that's inconsistent is in the very, very last row. So the only hope that I have, it's like talking to Obi-Wan Kenobi, you're my only hope. The only hope that we have is the 2g plus k plus h. Man, this thing better be 0. Because if it's not, game over. It's inconsistent. Because I got to avoid a bunch of zeros in something that's not. Okay, so for consistency, Consequently, for inconsistency, just make sure that it's not 0. Lots of different answers there. You have 3 variables, 1 equation. You have 2 free variables in play. Okay, let me stop there so it makes sense.
Yeah, I think I got it. It's
Good. All right, let me grab your other one, take a look at it. Construct an augmented matrix. We just talked about that, didn't we? Construct 3 different augmented matrices for the linear system. Okay, so we have x1, x2, and x3. Okay, so this is the solution set at the very end.
right.
Okay, so what that would mean is if I was going to take my augmented system, hit it with some good old RREF, row reduced echelon form, you would eventually come up to this right here. That would be your answer.
Mm-hmm.
Okay, so if I want to construct an augmented matrix, we'll just do some raw operations. Suppose I take row 3 and I add it up. So I'm going to jumble it back up again.
Yeah.
0, 1, 1, 1, 0, 0, 1, 0. And let's add up to the first row too at the same time. Then let's maybe take row 2 and let's just throw it down to row 3 just to spice it up a little bit. And let's add up to row 1, just because we can. There's a system. Interpret the results. x1, x2, and 2 copies of x3 equals -1. Now the second row tells me I'm going to have x2 plus an x3 equals 1. And the last one tells me x2 plus 2 copies of x3 equals 1. There's one system. So here, I know what the outcome is going to be because it's a solution. It's always going to look something just like this. Then I can jumble it up however I need to. Just unsimplify, in other words.
Yeah.
Okay, that's kind of a fun problem there. So you can keep doing this 2 more times and get your system.
Yeah. Okay.
Now, is there anything about these 2 problems you're not for sure about?
Um, it makes sense. I guess for the first one, like, for that one, you multiplied the top row by 2.
Mm-hmm.
And did you just, like, is that something that you recognize just because, like, the bottom row had the -2 and the top row had the 1?
Yeah. Now, whenever you're going through row operations, here's probably what they're going to teach you. They're going to say, you're going to always have to take this and pivot down. You go from row 1 to row 2, then from 2 you go to 3. And what they're going to try to do, if that's the direction you're doing, is they're going to try to get you a block full of zeros right here. They're going to try to get you a block full of zeros right there in this kind of algorithmic procedure.
Mm-hmm.
Now, you don't always have to do that.
Yeah.
What you're trying to do in the very end, whenever you're doing something called solving the system, you'll probably talk a bit more about this in your class later on, is you're going to put in something called RREF. It stands for row reduced echelon form. And if something's in echelon form, it's going to look something a little bit like this. You have some number here, 0, some number here, 0, and maybe a number over here. But the main thing is you create what's called a staircase pattern. See, in linear algebra, there's a lot of German terms in it. And that has to do with the fact that linear algebra was really starting being studied during the late 1800s when a lot of proficient mathematicians were over in Germany. But eventually, those mathematicians left. You know why they left? World War One, World War Two.
That
Yeah,
would
those
make sense. Yeah.
they dispersed immediately afterwards. Einstein,
Yeah.
Germany. You hear that dramatic term there. Uh, Other things like sure, and you hear a lot of these. They came over here to the States where they really helped out with the war effort with their math skills, their phenomenal brain power, and helped us win the war, I guess. Uh, but you hear a lot of the German influences, echelon form, eigenvalues, eigenvectors, and you hear it in the back of your throat when you're speaking in German. Now, like with calculus, you hear a lot of the English and French tones within it. Integrals, you talk a little about the natural log. It's ln, but it's natural log. Why is it not nl? Because the French, they do a little backwards than what we do here, so that's why. But for them, it's perfectly fine. It makes sense. For us, like it's a little backwards, but it's like house is red or casa de rojo. So it just kind of depends on your language. But when you're looking at echelon form, you're creating this staircase pattern. So if I was to have a number down here, like 1 and 0, it's not quite there yet. Because what you're going to do is find what are called pivot positions, leading entries, and everything below leading entry needs to be 0 to be an echelon form. So you have to multiply something with row 2, and you do what's called pivoting down. Take the results and drop it down. Now, in a textbook, they do talk about things called pivots. In this kind of a class, it's not really all that important to talk about pivots unless you're talking more about like a numerical analysis kind of a sense. So when you see that, you need to start thinking of things like leading entries. They're kind of synonymous with what we're talking about here. And a leading entry is an entry, like if I take this matrix up here, in which everything to the left of it is 0, and everything below it is 0. I don't really care about the top. That would just indicate there's a leading entry in the second column. Everything to the left, what about below? Are all my zeros, are they all zeros? Or by default, remember back from discrete math, false implies I don't care, it's always true. So that would say by default, the back of a statement, everything below it is zeros. Oh, it's not really zeros there. But so that would also be a leading entry. And likewise, everything to the left, there is no to the left. So by default, again, it's true. Yeah, that's going to correspond to leading entry. Now, for getting in what's called reduced echelon form, that's when you want to go a little further and start putting zeros on top. And you got to make sure that all the leading entries are all 1. That gets you what's called RREF. Now, in your textbook, let's see if we can try to find it here. That's going to be on page 14. Right there. So look at example 1. You see how I have those boxes, they have those asterisks. The asterisk is just saying it's just some value out there. They're just not going to tell you what it is. The boxes are saying it's just something that's not 0. If you look down below, the B and RREF, look at the differences with echelon form and RREF.
yeah.
What do you see?
So it's one. So it's ones instead of like above the staircase. It's all
Yeah.
ones.
Yeah. So one's on the, as you go up
But
from the bottom, the first
yeah,
non-zero entry is going to be 1. Right.
yeah,
Anything above it is also going to be 0.
yeah.
So if it's a pivot leading entry, everything above and below and to the left, 0. And the only instance in which you're going to have a non-zero above is because there's no leading entry there to knock it out. That's what's happening
Right.
there.
Okay.
Okay. So here's what you need to do is you need to really spend some time going through this by hand. It's it's easy to understand, but man, really getting it implemented is going to take some time to really hammer that out, that skill set.
Yeah.
Okay, now let's pause that and see if you have another question besides these two.
Let's see. Um,
Oh wow, look at that. Augmented matrix. Okay, so it's not in echelon form quite yet. What would you need to
yeah.
do to get this in echelon form?
So the this wait, no. Yeah, this should be a one. This would have to be a zero.
Right, just switch those two rows up.
Yeah. Yeah.
And now it's in echelon form. Now, row operations will not influence your solution space. So it's going to be the same. So what do row operations really do? What are they really doing? You're looking at a system, take it back to pre-calculus, algebra 2 if you like. You would, instead of doing a substitution, you might do like an elimination procedure. Multiply by -2. Joey, that's a row operation. Multiply a row by a value. And then you would take the equation, you would add it down. That's a row operation. So row operations really are talking about what's called in algebra 2 known as the elimination procedure. And when you start back substituting up, getting into RREF, going backwards with it, that's like doing the substitution procedure. Okay, so
Oh
here we
yeah.
have an augmented matrix. We'll put the line in so you can see it. Is it consistent?
Don't we have 0, 0, 0, -1?
Oh, that's exactly right. Inconsistent, game over, right there. There is no solution.
Yeah, that makes sense.
Okay, let's take a look at your next one. Oh, there it is. All right, Joey, here's what you're gonna have to do. Form your augmented matrix. First equation, 1, 4, 1, 5, 0, 1, minus 1, 1. 3, 15, 0, 12. Okay, I want you to stare at this system. I want you to think about what you might be able to do to start putting this into echelon form.
Well,
Okay, we gotta create that staircase
could,
pattern.
yeah, so
So I want to
with,
alleviate some of these values.
yeah, so I guess we could do, I mean, you could multiply the top row by like -3 and then add it to the bottom row.
Okay, give you a little hand here. -15, 12. Okay, what can you do next?
The middle and bottom row are, if you just multiplied the middle by -3,
Yeah.
when we get, you know, and then if you added them,
What's that tell you then?
0, 0, 0, -6.
Now,
Um,
remember that visualization I gave you earlier with those textbooks,
yeah,
planes. You can get that common point of intersection. You have a common point of intersection that necessitates consistency.
consistency. Yeah,
Do I have consistency?
no.
There's no common point. Now, I want you to take a look at this again and see if you can find a faster and easier way.
Okay. Um, no.
Here's what I do. I look at the third row and I see that it's all multiples of 3.
Oh yeah.
Let's divide
Oh
it out.
yeah.
Then I see a little bit easier. I subtract it off. Multiply the first row by -1 again.
Mhm.
0, 1, -1, -1.
Yeah.
Oops. Yep, like there.
So would that also, like, wouldn't that show you an inconsistency?
It sure would.
So you don't even have to go all the way.
You would take maybe because these two are not the same. You have maybe negative, positive, negative, add down. 0, 0, -2 again.
Yeah.
It's that same issue. So as you're maneuvering through your row operations, you want to look for patterns within it. What they're
Mhm.
probably going to teach you again is you're always going to pivot first to second, second to third, and then all the way down, then do it again for the next one. You could. Sometimes it's more complicated to do that
Yeah.
because here's what some people will do. They'll say here's 3, 0, 1, and they'll say here's 1, 2, 3, and 4, 5, 6. Some people will say you take the first row and you're going to divide that. You could. And then multiply by negative, and then you're going to take this and you're going to add it down to the second. You could, but do you
Yeah.
see where this is becoming hard?
Yeah.
You're going to do some fractions.
Actually,
I don't recommend it. I would take the second row. I might multiply by -3. Yeah, that might take it and knock the first row out. There's no reason why I couldn't do it. See, here's the thing. You're in the driver's seat. It's your problem. You do as you wish. Maybe this is the better route to go. Time will tell. Now, the reason why people tell you that has things to do with partial pivoting and mainly because that's how they were taught too, and they don't know any other way of how to go about it because this makes sense to them. That's how they're taught, but it's
hmm.
hard.
Yeah.
Find
That's,
find the easier path if you can through these.
yeah.
You get the same
That's
solution at the very end.
fine.
Because here's what RREF means. RREF is synonymous with the word solve. So if you solve the system, RREF. And if you solve a system, how many solutions? Well, how many different answers should you get?
I
Well, it
mean,
should all be the same.
I guess I should just be one.
Yeah, you should have one answer. You shouldn't have this answer, then that answer, and that answer, which are all
Yeah.
contradictory. Otherwise, it's not consistent.
Yeah.
So a good true false question, and that happens on these kind of exams, true false questions, concept questions. That's what makes this a little bit more challenging in other classes, is RREF has one. There's only one RREF for every system. But
Okay.
if you notice, there's a lot of different echelon forms which are possible,
Yeah.
not just one. So REF is unique, echelon form's not.
Yeah. Okay, that makes sense.
Good. Well, Joey, throw your next one up. This is fun. Let's take a look at your next one. Okay, so tell me what's going on here.
So we need to find the value of h to make it consistent. Um,
So what's your plan of action?
well, I guess we want to be consistent. I mean, if we multiplied, uh, if we multiplied it by 3, then the sixes would be the same. But
Now, determine something that's consistent. Remember, we gotta worry about that row again. 0, 0.
0, yeah.
Okay, so that's our plan of action.
So we should try and get that.
So let's see if we can get down to something like 0, zeros, if I can. Now,
Okay.
once again, we're talking about an augmented matrix, and let's just put a line there just to help us separate it out. Separate the wheat from the chaff, I guess I would say. Take the first row, maybe multiply it by -4.
Yeah.
-4 times 2, -8, plus 6, -2. Actually, would this right here ever be 0, this -2? No, that's never going to be 0. But look right here. What is that?
Yeah. If H is 5.
H is 5. Now, I'm going to take the problem, I'm going to change it up a little bit more. Let's say if I had this right here. And notice how that top row really didn't matter.
Mhm.
Suppose if I actually had a k here, k plus 3. What values for h and k would I need for this to be consistent?
So I guess then if you did have, so if H was 5, then K would have to be -3.
Okay.
And then otherwise,
Think of all the values.
I mean, if it's,
If h is not 5, k could be whatever you want.
yeah, then it could be anything.
Any real value.
Yeah,
If h was 5,
K can't be -3.
it's got to be -3.
Yeah,
Otherwise, you're going to have problems.
yeah.
So what would it then mean to be inconsistent? If one inconsistent, I don't want to avoid this anymore. I want that row.
And you'd have to have H be 5 and K be anything except -3.
K is any value except for -3.
Yeah,
And that's it.
okay.
Okay, so you're going to see a lot of these kind of problems. I would expect something like this maybe in your exam or some concepts related to it. Remember, you're either going to avoid or you're going to look at that kind of row. 0, 0, and not 0. Good. Joe, I
Okay,
think we got time
yeah.
for one more here. I'm throwing another one up.
Yeah, let's see. Uh, this is the only other one that I have.
Oh, look at that picture. Intersection of those lines.
And it just, yeah,
It's consistent.
yeah,
Interpret this in terms of a matrix. 1,
okay,
3, 9. 1 minus 1, 1. Okay, with some good old RREF. Or reduce it. Let's see what you do.
well, so that means we'd want, if I multiplied, don't I want, in, if I want it to be RREF, then wouldn't I want the top one to be 0, like the top left?
Well, we can multiply the first row by -1 and
-1.
pivot down.
Yeah. Yeah. So then, but do I want to keep it like,
Yeah, go ahead and multiply the first row by -1. Let's just do that. Write our steps out.
okay.
Add down the row
All right,
2.
add
What
that
do you get?
down. I get 0, -4, and then -8.
Okay. Now, simplify as you go. Take the second row. What's the common term?
Or 4. Yeah.
Okay, so we'll pull that out. Divide by -4. 1 and 2.
Yeah.
How you can get a 0 up there for the -3?
You could multiply the bottom one by 3 and then
Let's do it.
add
Pivot up.
yeah,
Okay, what do you get now?
-1. Yes, you get
And then multiply this by negative. So it's a 1. Now, the reason why you want to do that is because if I gave you this and asked you to solve for x1, you would say, well, it's not solved yet. You would get a +1.
yeah.
So when you put in RREF, it's synonymous with solve for the variable or variables.
Right.
Point of intersection, 3, 2. Good. Well, Joey, how do you feel about things for today?
Pretty good.
Pretty excited?
Yeah, it seems like it's gonna be fun.
It's going to be fun. Now, you do have to do some work, but it's going to be a
Yeah.
blast. Remember, you're going to have to know definitions. So here's what you need to study is make sure you know what it means to be consistent, inconsistent. Make sure you have a good working understanding of the definition. Now, some definitions you really got to know verbatim, but consistency and inconsistency, just working knowledge, as well as augmented matrix. We get something called a span and a basis later on, and you will get there. That's when you really need to know like verbatim what the actual definition is to work the problems. But we'll talk about those as we see them, as they pop up. I'll show you which ones you need to know. But yeah, it's going to be a fun time. Hang in there. You'll feel that linear transformation, and that makes a lot more sense later on. It's a great joke. It's just it doesn't make much sense now. But later on, you'll feel that transformation. You'll get there. All right.
Yeah.
Well, Joey, it's great seeing you again. I look forward to this term. I think it's going to be a good class for you. If you need anything in the meantime, just let me know. Otherwise, I'll see you next Thursday.
All right. Sounds good. Yeah.
All right. Take care.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.